All right, hello. Okay, so we ended here on part one, so let's go over. Nope. Okay. Okay, so pain, okay, is obviously set by neurons, so we can control those neurons and we can inhibit pain. Okay, so let's take a look at. Well, I should skip forward to this slide. This slide explains. This slide explains the previous slide a little bit better. Okay. Okay. So if there's no stimulus, there's no pain coming through. Okay. So this inhibitory neuron is usually on. Okay. So no pain. Okay. So when there is pain, that signal comes from the C fiber. The C fiber actually inhibits the inhibitory neuron, which negative of a negative is a positive. So the inhibition stops, and you get this stimulus to the brain. Okay. However, the AB fibers, okay, can actually stimulate the inhibit, like turn this on a little bit. The A beta fibers can actually, and those are the touch receptors, can actually turn this on a little bit, which will modulate pain and make it less. That's why, like if you get hurt, like rubbing that area makes it feel less painful. That's why. Okay. All right. Chemoreceptors. Okay, so this stuff you should already know. Okay. Um, okay. So here's the olfactory pathway. Again, you should know all this stuff already. Um, okay. You should know all this stuff already. Okay. Okay. So what's related to smell is often taste. Okay. Um, what we consider odor receptors and what we consider taste receptors are in reality the same type of receptor. They respond to the same type of things. Chemicals that are dissolved in mucus, one way or the other. The only difference really is location and density. Okay, so taste actually plays a huge role in smell plays a huge role in taste. Like if you can't smell anything, everything tastes bad. Okay. All right. There you go. Okay. So the olfactory neurons, okay, grow back every couple of months. So the mucus has to dissolve in this layer, and then you have signaling through these bipolar neurons that go up to the olfactory bulb, okay, and send the signal to the olfactory. Okay, there is a glomerular nasal organ in rodents that responds to sex pheromones. This does not actually exist in humans. Okay. The way smell works, we have a bunch of different receptors. We have about 100 different receptors for smell. Rats and mice have thousands, so they have a much more precise sense of smell. But it's not like we only smell 100 things. We smell different receptors with different smells would trigger many different receptors. And that combination of receptors is actually what we smell. Okay. Okay, so you see that there. There are 5 basic tastes. There's actually a little bit more than that. They're discovering more and more. But there's 5 basic tastes. sweet, bitter, umami, sour, and salt. Okay. And then, so here are how everything works. Okay. The surface of your tongue. Okay. This is the surface of your tongue, but the surface of the tongue has to be rough, right? So it can't really handle all these receptors. So what happens, all these receptors are, they lie underneath the surface, and the only thing coming through is a tiny little hole called a taste pore. And the taste pore has these receptors on it. Okay. The sweet receptor, for example, will bind sugar molecules. The salt, the bitter receptors bind things that are bitter, like caffeine, stuff like that. Umami binds monosodium glutamate. Okay, sour binds H plus, and it triggers a response. Okay. Okay. So okay, so it's all the same thing, right? Sour, sweet, umami, and bitter. They bind to specific protein ligands here, and that triggers a calcium response. Sour binds. Sour is acidic. Acidic things taste sour. Acidic things also have H plus. So H plus is what goes through the membrane and can causes the same calcium release, um, and causes the neurotransmitter release here. Okay. Okay. 2.3 hearing. So let's talk about hearing. Okay. So hearing is our perception of energy that's carried by sound waves. Okay. Sound is the brain's interpretation of the sound waves that reach the ear. Frequency is translated in pitch. Frequency is measured in hertz. Okay, the actual frequency is measured in hertz. We hear it as a pitch. Frequency and pitch are roughly the same. They're not exactly the same. They're not like one-to-one translation of what frequency is and what pitch is. Okay. Loudness is an interpretation of intensity, a function of the wave amplitude. So, okay. So let me explain a little tiny bit of physics. Okay. So you have sound. This is a sound wave. Okay. If it's the same sound, like the hills should all be the same. Like I can't draw. Okay. But here's the important things. Okay. The frequency is measured by distance from there to there. Okay. Actually, to be more precise, it is measured from top to top. Okay. That is a frequency. Okay. How many times this wave occurs per second is the frequency. Okay. Hertz is 1/seconds. So something that has frequency of 100 hertz, it has moved through the medium at 100 waves per second. Okay. The height of the wave is measured in decibels. And that's the amplitude. Okay. All right. So the okay. So wavelength amplitude So these two things have the same amplitude, but they have different wavelengths. Okay, so we hear them as different pitches. Okay. All right. So basically, if sound comes through, vibrates, all this stuff, you should kind of know that all this stuff from anatomy here. Okay, so we'll go talk more about the physiology of it all. Okay, so here is what happens if you if you take this and unroll it here, that's what it is. Okay, so there are these hair cells that are on the membrane here. Okay, these hair cells. Okay, when these hair cells, okay, when they vibrate, the hair cells will, like when you hear a certain frequency, a certain cell will vibrate. Okay, and so you'll see that action potentials increase. Okay, and that will generate. That will be how you hear that particular pitch. Okay. Okay. So the coding for pitch is a function of the basal membrane. Um, okay, which cells vibrate? Um, which cells vibrate tells you what pitch it is, how much they vibrate, how many action potentials it generates. Okay, tells you how loud the sound is. The cell will vibrate more and generate more action potentials if it's louder. So so that's how it works. Okay. Okay. So here's the basal membrane. The basal membrane um, has high pitch sounds and low pitch sounds along as like the hairs get longer. Um, and so the high frequency, the longer hair cells are going to respond to a higher pitch. Okay, the lower frequency cells are respond to lower pitch. Okay, as adults, we tend to lose the high frequency portion, and therefore we can no longer hear high frequency noises. Okay. Okay. Coding pathways. Okay. Okay. There are two types of hearing loss that you have to be aware of: conductive hearing loss and sensory neural loss. Okay. Conduction hearing loss is loss of transmission. Your inner ear works fine. The pathway of sound is somehow blocked. Okay. Like if you take a cotton ball, you shove it into your ear. You're blocking the passage of sound through your ear. Okay, that's conductive hearing loss. Okay, um, sensory neural hearing loss is damage to the inner ear, the cochlea. Okay, and then central hearing loss is even worse. It's damage to the cerebral cortex or the pathway that the inner between the inner ear and the cerebral cortex. Okay, usually we consider this as part of sensory neural. This is the neural part of sensory neural. Okay. All right. Okay, the ear. So equilibrium is a state of balance. Okay, so there's two types of equilibrium here. Okay, one is static equilibrium. Static equilibrium tells you the position of your head in space. Okay, where my head is positioned in space. Up, putting down, putting left, putting right. Okay, where my head is in space. The other one is rotational equilibrium. Rotational equilibrium has three planes, and you can rotate in three directions. You can rotate x, y, y, z, and x, z. Okay. Okay. So the ones that are responsible for static equilibrium are the otolith organs, the sacral and unical. And then the ones that are responsible for rotational equilibrium are the semicircular canals. Okay, the otolith organs sense linear acceleration in head position, right? So static equilibrium. The semicircular canals sense rotational equilibrium. Okay, so let's talk linear equilibrium first. So linear equilibrium is located in the macule and saccule, and they look exactly the same. And they have all these little otoliths. Okay, these otoliths are little knots of calcium. Okay, but because they're little knots of calcium, they're heavy and they're like little rocks. That's what otolith actually means. Okay, little rocks. What they do is they have gravity, right? So if your head is straight up and down, then gravity pushes it straight down, right? The floor is straight down. If I bend my head, okay, the rocks pull to one side and pulls the head to one side, and that changes the firing rate of these cells, and that changes when it changes the firing rate. It makes it go slower or faster. If you tilt your head forward, it actually fires faster. If you tilt your head back, it fires slower. Either way, it sends information to your brain that you're firing faster or slower. Okay. Uh, and then here are semicircular canals. Okay. The semicircular canals. You have three, right? So X, Y, Y, Z, X, Z. Okay. What they measure is equilibrium, rotational equilibrium. Okay. So if you're not moving, the fluid inside the ear is not moving. Okay. If you start to spin, when you accelerate, you move first, then the fluid moves. Okay. So that if you move faster than the fluid, that tells you you're accelerating. Okay. But eventually, if you keep spinning, the fluid will keep flowing the same way at the same speed as you are. Okay. Um, when you stop, the fluid will keep going, and that tells you you're slowing down. If the fluid is moving the opposite, if you're not moving, but the fluid is, that tells you you're slowing down. And I'm sure you guys will do this in lab. Hopefully, you guys would. Hopefully, by the time like you guys see this recording, you guys are already back on campus doing this stuff in lab. But basically, you spin yourself in a chair, and suddenly stop. The fluid inside your ears keeps moving, which is why your eyes keep twitching, and which is why like all this works. Okay, and that's why you're just okay. All right. Chapter 3, part 3 will cover the eyes. The eyes are a big deal, so we'll take my time and explain them in a separate unit. Okay.